Welcome back to Calculus 1. In the previous lesson, we used the properties of limits to evaluate limits analytically. We saw that direct substitution works for many familiar functions, and we learned several methods for handling the indeterminate form 0 over 0. In this lesson, we will give a name to the property that makes direct substitution possible: continuity. We will learn what it means for a function to be continuous at a point, distinguish between removable and non-removable breaks, and use one-sided limits and apply the intermediate value theorem. Let's get started. Here's what we will cover in this lesson. First, we will state the three conditions required for a function to be continuous at a point. Next, we will examine breaks in a graph and decide whether each break can be repaired by defining or retaining the value at one point. We will then use one-sided limits to analyze functions at seams, jumps, and endpoints. Finally, we will use the intermediate value theorem to guarantee that a continuous function reaches particular values, including a value of 0. Continuity is the property that makes substitution works. The shortcut we used in the previous lesson now receives a precise name. A limit asks where the outputs are heading as the input approaches a particular value. Continuity asks an additional question: does a function actually arrive at the same value? The graph on the left has no break. As we trace the graph from left to right, the curve continues in one unbroken stroke. The graph on the right has a break at a single input. The open circle shows the value approached by the surrounding graph, while the solid point gives a different function value at that input. Informally, we say that a continuous graph can be drawn without lifting the pencil. This is a useful picture of continuity, but it is not a reliable mathematical test. A graphing screen can hide a tiny hole or another important detail. For a precise test, we need the three conditions on the next slide. A function is continuous at a point when three conditions hold. First, the function must be defined there. In other words, there must be an actual function value at that point. Second, the limit at that point must exist. The function must approach the same finite value from both sides. And third, the limit must equal the function value. Although the third statement presumes that both the limit and the function value exist, we list all three conditions separately because they identify the three distinct ways continuity can fail. Continuity is a local property. It describes what happens at one particular point. A function is continuous on an interval when these conditions hold at every point in that interval. For a continuous function, we may find the limit by direct substitution. That is the practical benefit continuity gives us. This slide illustrates the three ways a function can fail to be continuous at C. In the first graph, the function has no value at C. There is an open circle but no solid point, so the first continuity condition fails. In the second graph, the two sides approach different values. Because the left hand and the right hand limits disagree, two-sided limits do not exist. The second condition fails. In the third graph, both the limit and the function value exist, but they are different. The surrounding graph approaches the open circle while the actual function value is given by the solid point. Therefore, the third condition fails. Each picture breaks continuity in a different way, and each failure suggests a different question. Is there a value at the point? Does the limit exist? And do those values agree? We now divide discontinuities into two broad categories. A break is removable when the graph has a hole that can be filled by assigning the appropriate value at that single point. The test is straightforward. Determine whether the limit exists at the break. If the limit exists, use that limiting value to fill the hole. The function then becomes continuous at the point. If the limit does not exist, the break cannot be fixed simply by filling in one point. The surrounding behavior of the graph would have to change, so the discontinuity is non-removable. The graph on the left shows a removable hole created by a cancel factor. The graph on the right has a vertical asymptote, which cannot be repaired by inserting one point. Removable breaks are often algebraic leftovers. A factor cancels, but the original formula still excludes one input. Let's classify the three examples on this slide. In part A, factoring reveals a common factor that can be canceled. At -1, the limit is -6. Therefore, the break is removable, and assigning the value -6 fills the hole. In part B, Factoring again reveals a common factor. After canceling, the simplified expression helps us analyze both excluded inputs separately. At -3, the limit is -1/6, so that break is removable. At +3, the function decreases without bound from the left and increases without bound from the right. The two-sided limit does not exist, so that break is non-removable. In part C, the left-hand limit is -1 and the right-hand limit is +1. The sides disagree, so the jump at 4 is non-removable. One function can contain both removable and non-removable breaks, as we saw in part B. We must check each suspect point separately. Now it's your turn. For each function, decide whether the break is removable or non-removable. If it is removable, determine the value that would repair it. For the first function, examine the break at 3. For the second function, examine -2. And for the third, examine 1. Begin by filling the limit at the indicated point. If the limit exists, the break can be repaired by assigning the value to the function. If the limit does not exist, changing one point will not help. Pause the video now and work through all 3 examples, then continue when you are ready to check your answers. Let's check the answers. For problem 1, factoring and canceling produce a simpler expression. The limit at 3 is 6, so the break is removable. Assigning the value 6 at the missing point makes the function continuous. For problem 2, the values decrease without bound from the left and increase without bound from the right as the input approaches -2. The two-sided limit does not exist, so the break is non-removable. For problem 3, the left-hand limit is -1 and the right-hand limit is +1. Since the one-sided limits disagree, the two-sided limit does not exist. This is a non-removable jump. Every problem came down to the same question. Does the limit exist? If it does, the break is a hole we can fill. Sometimes we need to examine only one side of a point. A right-hand limit describes the value approached when the input moves towards the point through values on its right. On the graph, we follow the right-hand branch toward the point. A left-hand limit describes the value approached through inputs on the left. We follow the left-hand branch toward that point. The small plus or minus in the notation, here and here, records the side from which the input approaches. It does not tell us whether the function values are positive or negative. All the familiar limit rules still apply to one-sided limits, including the rules for sums, products, quotients, and the squeeze theorem. At a jump, the two one-sided limits answer 2 separate questions and may produce 2 different results. Let's look at 3 situations in which one-sided limits are especially useful. The first situation occurs at an endpoint. The square root expression is defined only at the right of 5. The right-hand limit is 0, and there are no domain values immediately to the left from which to approach. The second situation occurs at the seam of a piecewise function. From the left, the limit is 6. From the right, the limit is 1. Because the two one-sided limits disagree, the two-sided limit does not exist. The final example uses the greatest integer function. This function returns the greatest integer less than or equal to the input and jumps at every integer. The third situation occurs at a jump. As the input approaches 2 from the left, the limit is 1. From the right, the limit is 2. Again, the two sides answer different questions. Endpoints, seams, and jumps are handled in the same way. Answer each side separately, then compare the results. This equivalence gives us the exact relationship between one-sided and two-sided limits. A two-sided limit exists precisely when the left-hand and right-hand limits exist and approach the same value. Reading from left to right, if the two-sided limit exists, then the two one-sided limits automatically exist and agree. Reading from right to left, we can establish a two-sided limit by evaluating the two sides separately and showing that they approach the same number. This is particularly useful for piecewise functions. The same relationship gives us a clean way to show that a limit does not exist. Calculate the two one-sided limits and show that they are different. Continuity can now be restated with three equal quantities: the left-hand limit, the right-hand limit, and the function value at the point must all be the same number. At an endpoint of an interval, the function has only one side from which to approach. A function is continuous on the closed interval from a to b. When it is continuous at every interior point, right continuous at a and left continuous at b. Consider the square root function shown on the slide. Its domain is a closed interval from -4 to +4, and its graph is the upper half of a circle with radius 4. At every point inside the interval, the function is a composite of continuous functions. At the left endpoint, the right-hand limit is 0. At the right endpoint, the left-hand limit is also 0. Both limits agree with the corresponding endpoint values. Therefore, the function is continuous on its entire closed interval. Now let's choose the constant a so that this piecewise function is continuous everywhere. Each individual piece is a polynomial, so each is already continuous wherever its own formula applies. The only possible problem is at the seam at 2. Because the first rule includes the seam, use it to find the actual function value. The function value is 5, and the left-hand limit is also 5. Approaching from the right, we use the second rule. For continuity, its limiting value must also be 5. Setting the right-hand result equal to 5 and solving gives a equal to 1. A common mistake is trying to make the two formulas identical. That is not necessary. Only their values at the seam must match, together with the actual function value. The limit laws also tell us how continuity behaves when functions are combined. When two functions are continuous at a point, their constant multiples, sums, differences, and products are also continuous there. Their quotient is continuous as long as the denominator is not 0. For a composite function, the inside function must be continuous at the point, and the outside function must be continuous at the value produced by the inside function. This explains why the two composite examples on the slide are continuous everywhere. Our everyday list includes polynomials, rational functions wherever their denominators are non-zero, radicals on their domains, and trigonometric functions wherever they are defined. In general, the familiar functions we encounter are continuous at every point in their domains. For example, cotangent is continuous on each interval between consecutive multiples of pi. The intermediate value theorem describes an important consequence of continuity. Suppose a function is continuous on a closed interval. If we choose any height between the function values at the two endpoints, then the function must reach that height at least once somewhere in the interval. In everyday language, a continuous function cannot move from one height to another without passing through every height in between. The graph shows that the function may reach the same intermediate height more than once. The theorem guarantees at least one point, but it does not tell us exactly where that point is. Continuity is essential. A function with a jump can move from below the chosen height to above it without ever reaching it. The height example at the bottom gives the intuition. If you were 4 feet tall at one time and later became 5 feet tall, then at some moment in between you were exactly 4 feet 7 inches tall. Let's use the intermediate value theorem to show that this function has a 0 between 1 and 2. The function is a polynomial, so it is continuous throughout the closed interval from 1 to 2. At the left endpoint, the function value is -2. At the right endpoint, it is +6. Because 0 lies between -2 and +6, the intermediate value theorem guarantees at least one 0 somewhere between 1 and 2. We can narrow its location by checking midpoints. At 1.5, the function value is positive 8.875. So the 0 lies between 1 and 1.5. At 1.25, the function value is approximately negative 0.797. So the 0 lies between 1.25 and 1.5. Each check cuts the interval in half. This process helps us approximate the 0, although the theorem itself guarantees existence rather than providing an exact formula. The key pattern is continuity on a closed interval together with a change in sign. Let's bring the main ideas together. For continuity at a point, 3 conditions must hold. The function value must exist, the two-sided limit must exist, and the two must agree. A break is removable precisely when the finite limit exists. Assigning that limit value to the function repairs the whole. If the limit does not exist, changing one point cannot repair the graph. One-sided limits allow us to analyze seams, jumps, and endpoints. A two-sided limit exists exactly when the left-hand and right-hand limits exist and agree. On a closed interval, continuity gives us the intermediate value theorem. A continuous function cannot skip any height between its endpoint values. In the next lesson, we will study functions whose values grow without bound and learn how to describe infinite limits. Thank you for watching. In this lesson, we defined continuity, classified removable and non-removable breaks, used one-sided limits, and applied the intermediate value theorem. In the next lesson, we will examine infinite limits and vertical asymptotes. I'll see you there.